All right. Admin to Code 2024, Day 8. Resonant collinearity. So the setup for this problem is that you're given a map like this, and each of these letters and numbers, and they could also be lowercase, they are antennas giving off a frequency. The frequency is just it's kind of odd. It's like this antenna is giving off the capital A frequency, and then this is giving off the 0 frequency, and such and such for the rest of them. And the dots are just nothing; they're just emptiness. But it looks like that there's a resonant kind of frequency that shows up on the opposite ends of two antennas. So basically, since this and this, they're on like the same kind of path here, there's going to be it's called a resonant frequency, or actually they call it an antinode that'll show up on the opposite sides. And it's basically just following that sort of like y equals mx plus b kind of fashion. Let's see, so let's scroll down to what it would look like. So it would look like this. So we're gonna look at each antenna, get like the distance and that slope, and then put two of these antinodes on each side according to that. So this one and this one comes from these two, but then there's also this one and this one, so that creates well, I think that one would go out of bounds because it go out this way, and then actually the other one would sit on top of here. That's not a great example. So this antenna and this antenna, their antinodes are going to be here and here, and then this antenna and this antenna are going to be oh wait, no, maybe it's these two. This one goes down. Let's see, it starts here. Three right there. Yeah, so it's this one and this one. This is its antinode here, and then this one's antinode shows up here. And for each of these two antennas, we got to calculate these antinode positions. So yeah, I hope that made sense. To me, this problem was kind of confusing just to even understand what they were asking for. But it's just looking at each of these antennas that are the same frequency, and then taking that kind of distance that they have in the slope and putting a hashtag symbol on the opposite sides of them, and then doing that for each one. So that's part one. And I'll go ahead and go to the code now and show you what I did. So here I just have hard coded in the example one. So the main thing here is we're going to start right here. So what this function is doing is I'm actually just making like a hash map of each frequency. And for each frequency, where are the coordinates for that antenna? So this hash map would be like, oops. So for 0, it'd be at like, I don't know, 1, 2, 4, 5, 7, 0. And then for A, it could be 7, 2, 0, 1. That's just random. That's not the actual answer here, but that's just to sort of elucidate how this hash map will work. The key will be the frequency, and then the value will be a list of tuples of the coordinates for the antennas. And that's all this is doing. It's just going through through this matrix, this map of the antenna map. And then if what we're looking at is not just a simple dot, then we're just going to add it to our hash map called frequency maps. Okay. And then we actually need to start calculating, the positions of the antinodes. So, so we iterate through this hash map here. We have this variable combos. That's just a list of, I got this from the itertools, library. And so it's just going to take the values and just have a combination for each of those positions for the antennas. Right, so it was 1, 2, 3, 4, a little different. Then 9, 0. We'll get a list that's like, I don't even know, it's like 1, 2, 4, 3, right? That's 1. And then 1, 2, 9, 0. And then what is left? 4, 3, 9, 0. Right? Okay, so we look at each of these combinations, all right? Because we need to look at, for example, here and here, and then what would be the resulting antinodes that come from those positions of antennas. And we figured that out with this function I wrote called calc antinode, and it gives us 2 positions for the antinode. And then we're just checking if it's not out of bounds. We're going to add it to this set here, antinodes, so that we can keep track of the unique positions. And then I also have an update map function just to make things visual, and that helps a lot with debugging this stuff, but it's not extremely necessary. And we're doing the same thing with the second one that it gives us. Okay, so let's go look at calc antinode. So calc antinode, this one's a little messy here, but we're just taking in 2 antennas, antenna A and antenna B, and then we calculate a tuple of x, y, which is just the x values of the antennas of each antenna A and antenna B, and then the y values of antenna A and antenna B just subtracted from each other. Because then all we need to do is get the resulting antinodes is just, what is that difference in the positive direction and then in the negative direction, and then that's what we want. So yeah, I hope that made sense. I know it looks a little weird, but yeah, that's how it works. So let's see, anything else I should mention here? But yeah, so I'll show you what it gives us. Yep, and that's exactly what they're looking for in the solution here. The total being 14 unique locations for antinodes within the bounds of the map. And then I've actually have the map correctly visualized as they do. So that was part 1. So part 2 was a little trickier, but not too bad. Basically, it turns out that the antinode occurs at any grid position exactly in line with at least 2 two antennas at the same frequency regardless of distance. So all this really means is basically the same thing, but instead of just stopping at the two here, it's as long as it's within the bounds of the map, it's just going to keep going, right? So for this one, you know, it'll just keep going this way, keep going that way, keep going this way. And then it also wants you to count the antennas themselves. So that was the difference. So pretty much everything else stayed the same for my problem. The biggest difference was the calc antinodes function here. Let's see. Did not need this. Okay, so pretty similar here. Pretty similar here. But we're gonna go through every single combo and then get the nodes from this function of calc antinode. And then for every node in that list of nodes, if it's not out of bounds, we're going to add it to our set and then update the map. So what I realized you could do is just pretty much the same thing, get the X and Y of that's the differences between the two antennas. And then I just copy them over to different variables, throw that into our resulting list here that we want. This is going to be the result of our antinodes as an array. And then we have this function here while this variable here, antinode 1, that we're updating, while it's not out of bounds, we're going to update it to add X and add Y to its coordinates, and then add that new value, that new modified value to our list of antinodes. And we're doing the same thing. The only difference here is that this guy is going in the opposite direction, the negative direction. And it's going to throw that in there, and then we'll get that list of all the antinodes. Okay. Yeah, so I think that was pretty much the only difference there. Let's see what it actually gives us. 34. I think that was the right answer. Yep, 34 antinodes. So yeah, this one again, I was able to have a map drawn out of the resulting answer. It looks one-to-one with their input here. And my answer was 34, same as theirs. And this works just fine with the input that they gave me. And yeah, I'm pretty proud of this one. It actually wasn't too bad this time. And yeah, I really enjoyed doing this. If you have any feedback on ways to improve this or any criticism, or if you just want to, you know, share how you did it, feel free to do so in the comments. If you want to come on the show and talk about it too, that's okay with me. You can hit me up on Discord. Thanks for watching. Bye.